The next section is actually related because this is now up to this approximation with just taking the first term in the Taylor expansion. We are seeing that this is the whole envelope is moving, and the envelope is unchanged. It still have the same function. It just have the argument shifting according to this shift in space by this good velocity times t. This whole thing is moving in this velocity, right? But that's not the case actually if you are including higher order terms. And Jackson did that by using explicit examples of U. Okay, and now the math is complicated because once you set whatever U is, Jackson actually use a simple. Well, I mean, at least simple enough, as simple as you can. Envelope function is just a Gaussian, and it's not difficult to integrate, and especially in Fourier transform, there's a property that you probably should remember. If the function you want to take the Fourier transform is a Gaussian, then the Fourier transform of Gaussian is actually also a Gaussian. But a Gaussian in K. This is if you have Gaussian in X, then you get A that is a Gaussian in K. That derivation is quite straightforward. I think I did that in math physics. But I mean, you can just check that by taking derivation. I'm taking integration. The idea is now by a specific form of U, actually use this a Gaussian x squared divided by 2L squared. So basically, the delta x is like L, except that it has this 2. Just by convenience, it doesn't matter how you define that. And this almost sinusoidal oscillation is described by this cosine term in some cases. So this oscillate with this wave number, right? And then the profile is different by this Gaussian. And obviously, you want this L is much greater than this wavelength as 2 pi over k sub 0, much less than x, so that you have many oscillations within the envelope. Okay. The length of the L is, I mean, you just look at this Gaussian. This Gaussian function is basically you plot the Gaussian. And obviously, when x is 0, this is 1, right? Then when x is kind of L over L, I mean, if it's L, then this 2 cancel is e2, so this is e minus L, which is not too small, but it's getting small. But if it's 2L, then it will keep getting exponentially. It's actually super exponentially small. So I have to do the square of that because, right? So this is roughly the delta x. Right? If this is L, this is L. So you can say delta x is roughly 2L. And roughly, okay. And so that has a physics of like the delta x that we had. Okay. And now with that, you can put that because you have this. You have this I omega k term. You assume that you have a medium such that I think that you use a model that omega k. This is some constant mu 1 plus a square. So this is just he's choosing arbitrary omega, which is a little bit artificial. because as we just erase, there should be a linear term also. But I mean, maybe he absorbed the linear term in the omega nu already. So it's just to illustrate the physics of this wave is broadening. He's using this kind of omega, so you can put this omega in here. So that's therefore be a k square in here. And the idea is that because of this Gaussian, this you can use this to calculate 8, just like what we did before. I mean, there's extra complication that Jackson wanted to treat it more generally, so we keep the initial condition of partial u, partial t also, but then it set it to 0. So originally 7.91 is more complicated than what we did before. But after you set partial u, partial t is 0, so the second term is cancelled on 0 anyway, and then we are back to just the simple Fourier transform A of k is just like taking a Fourier transform, except that you have this 1/2 part. I mean, originally there's this Jackson write this as a 1/2 power, but then your part is imaginary part. I mean, a complex conjugate, so that's 7.92. But anyway, if we just want to discuss it qualitatively, now you just like taking the Fourier transform, you have to u, and then e to the minus dx. That's how you calculate the Fourier transform a as a function of k. All right, and now that is not difficult to integrate. You put this to here. Like I said, you have a Gaussian, and the Fourier transform of a Gaussian is a Gaussian. You have the complication that there's a cosine term. The cosine is you can write cosine as e to the I cx plus e to the minus I cx divided by 2. So basically, it's separate into two terms. One is has I case of 0x, the other is minus I case 0x. But you see that these terms has the same form as the original exponential function. So basically, you are shifting the k. So basically, you're shifting the argument of the exponential function by these two terms. But the original, if you just take into that function after the integration and do it quite easily, or look up the table or by online integrator, and you see that this should be a Gaussian. So we're not working that. I mean, if you do it by hand, it's just nothing but taking what we call this complete square of the argument and show that right away is a Gaussian. But if you just write down the answer from Jackson, so basically it's a Gaussian. You have two terms, like here, you have two terms. A factor of 2, and it's Gaussian in k minus L squared over 2. And then you have a shifted in k. One is k minus k sub 0 square, and the other is the other way around, k sub 0 square. So both are Gaussian in k, but they're shifted in different ways. All right. Now the complication is once you have this is you put it back to here. So this go into here, and the omega, this omega goes into here. And now you do another Gaussian integral. Because this is integration in k, this is a Gaussian in k, both of these terms. So you have two terms. Both terms are Gaussian in k. But then this omega has this constant term and another k squared term. And this multiplied by t also. So you can group all the k squared term. It's still a Gaussian. It's just shift argument a little bit. one of the shift is just the group velocity that we did before, because once you put in here, so this the d although this is k squared, but d omega dk is not zero. The dk is obviously this is you get a factor of 2r. You have mu a squared k, and then you evaluate case of zero. You have a case of either case of zero or k minus. Well, yeah, well, I think it's case of zero. Just case of zero. This will be the group velocity, right? Yeah, and so that is non-zero. You still have a group velocity, but then actually you have the this a is different from what we considered before. So this term is centered at case of zero because it's k minus case of zero. So you have a Gaussian, and L is assumed to be large, so this width is small. The width like that. Right. But then you have a second term, so centered at minus case of zero, and then you have exactly the same profile. Okay, so that represents two. Actually, they will propagate in different direction, opposite direction. So you actually, and that is because you choose the initial condition such that partial u partial t is zero. So then at large, I mean, at positive t, then it's basically this is a superposition of two waves at when they are getting together at one single profile, but for positive t, then they separate. One is moving in one direction, the other is moving in separate direction. So there will be two-way packet after for positive t. And the idea after you do the integration, which is again now straightforward. In principle, straightforward because everything is k squared. It's Gaussian. Everything is Gaussian integral. So the end result is you shift the argument plus you have extra phase coming out. So that is exactly what that is. Well, that is 7.79. So this one, so again, shifting all the integral, which is if I really work that out, it would take maybe half an hour. So u x t will be. The idea is that they are still Gaussian. And using Jackson's, you're taking the real part because this part is complex conjugate, which means it's a real part, and divided by 2. And the result is no, the 7.79 is just this one when you substitute this into here, this into there. And 7.98 is the result. The result doesn't have this. You already used the Gaussian integral, get rid of that. So there will be one term that is a Gaussian in space now because you're integrating k, so back to the x space, the exponential, or using Jackson's the exp exponential function. It's a Gaussian in space, but then it's moved in the group velocity. This one mu a square case of 0 and times t square. And then the Gaussian has a width. The width is no longer this one. It's no longer this square. 2L squared is 2L squared multiplied by a factor 1 plus I a squared mu t of L squared. So that's an extra factor in here in the width in this delta x, except that this becomes compact. So it's a little bit unusual if you are not familiar with this. So you have an exponential function, but then you have a complex base, complex argument, right? But the idea is still that this function is broader than of the original one. It's not just this one. So you can say that basically delta x it's the it's like here, so delta x is roughly the the argument of this one. So it's like the argument of L 1 plus I n squared mu t over L squared, or the x squared argument squared, the magnitude squared. But you know how to do this magnitude, compact magnitude square becomes real. So basically, real part times the imaginary part. So, imaginary part square. Yeah, a mu t over L. This is actually just L because this L divided by L squared is L. Multiplied the square of the. Okay, so this is still bothering by this factor, but because as t increasing to this, you have the extra term. As at t equals 0, you have this L. But later on, this profile will make it border, will make this envelope border because this delta x increase. But that's just one part. The other part is we divided by something similar, exactly the same form IA squared mu t over L squared is 1/2 factor. And what this factor did is the reverse of that. So this will increase in time. So basically, the envelope is bordering. This is getting complicated. So initially, it's a Gaussian profile. But at later time, it's the whole symbol by good velocity, right? Then the width delta x becomes larger, right? At the same time, the height of the profile reduced by this factor, and obviously it's not the same height. And the reason again is just simple: the conservation of energy. Assuming this wave does not have dissipation, so the wave energy should be conserved. You have a wave packet of waves, so you integrate over the whole wave packet. That's the total energy. As it propagates, the energy should be conserved. So as it get border, so the spatial extent is border, so the amplitude of this wave should decrease. The amplitude of the wave will decrease. And obviously there are other factors also. The phase, the wave is oscillating in also shifted frequency also. You have this exponential factor. This is the positive propagating wave, and then there's a shift in frequency also. This is okay. That's the first term now. Is for this one, and then let's just say you have another term case here. Change the minus case. So basically, it's we copy this term, but this pulse will. This is represent this pulse going in the positive x direction. So this one will represent another pulse going in the negative x direction. Okay, and it's okay. So that's I skip a lot of integration because those take time. So assuming the integration is correctly, then you get all these answers. But the physics is like that, just a simple conservation energy. And the reason that why it's bothering is because now you see that this wave is what we call a dispersive wave because we erase those phase velocity. This omega k, right? It's c over n. So if n is also a function omega or function of k, this becomes dispersive. It means that the phase velocity for different k or different omega are different. So this way, I mean, it's not exactly because it's not exactly a delta function. So it has a width. So depends on exactly where the k is. So you have the wave packet, but the component of this wave packet all move. The phase is moving in different direction. I mean, different values. The phase velocity is different, but then the group velocity is like d omega dk. It's also a function of k or omega. After you do the derivative, n is a function of k or omega. This also depends on the K also. So you can also separate the original profile in the different package. It's like the superposition of different package. Each package has different K, and because you have initially have different K in the profile anyway. Uh, so they move differently. So some is moving faster, some are slower. So then the initial profile will broaden because the faster way will extend it to it's moving more. So this is not just VG. This is VG as a function of K. So for the higher K, it moves faster. For the smaller K is moving slower. Not exactly the for VG with a K that is make it smaller, then it's moving slower. So the whole thing broadens. So you see that the broadening should depends on another derivative. So it's FDD VG dk. That depends on g square omega dk square. Right. So in this case, d omega dk is mu a square times k, and then if you take another derivative, then you get rid of that. So mu a square actually double derivative omega d square omega dk square. So basically, this is what it is. This is du a square. So this is omega double square. So you not using this model, but arbitrary omega as a function of k. Whatever could go into here is omega double prime. Okay, so that will be responsible for the bottoming. So this will be omega double prime. Right. So as long as the second derivative is non-zero, then the wave packet will broaden in time and then decrease in amplitude. So that's the physics of the dispersive wave. Is that okay? So that's of course this is all based on the assumption that talking about almost plane wave. It's just very broad uh, initially, and then the wave number profile is very sharp. It's like almost like a delta function. So therefore allow us to do Taylor expansion. If this assumption is not valid, it's this wave is just like a pulse. Initially, it's just a single pulse in space. Then obviously that will introduce a K profile that is really large. This A sub K will be, delta K will be very large. Then over this broad range of K, obviously the Taylor expansion of omega as a function of K will not be that valid. So all this thing, how it change will depends on exactly what the dispersion relation is. So that it's getting complicated. So all this argument might not work. So you have to take a little bit careful. So all the concept of good velocity and then the profile broadening and all that, it depends on the assumption that it's almost like a single frequency. If it is not, then you need to be a little careful, especially for more complicated media, right? In some situations, obviously, some media actually you can include a nonlinear consideration with some of these powers actually doesn't disperse. This is called solid time or solitary. The profile actually doesn't change in time if you take into nonlinear term in the wave equation. Mm. Okay, that is the end of 7.9.